So before moving out, can I give you some more instructions? So you can collect the tea coupon from Mr. Arun. He is waiting over there. You can collect two tea coupon. One is for morning and one is for evening. And I hope you all received the lunch coupon. If you have not received, please collect it from the registration desk. And the keynote session and the panel discussion is happening in auditorium 2. After tea break, the session is going to split into two. One is big data technology track and big data analytic track. So in auditorium 2, big data technology track is happening, and in auditorium 3, that is the hall which you are sitting now, big data analytic track is happening. So you can keep the answer sheet in your seat and you can move out. So those who came late, they can take 5 more minutes.
And nowadays, it's a worldwide collaboration with more than 10,000 users from all over the world. You can see that India is one of them. And I wanted to add this slide to say that, well, India is now in the status, so it's an observer state at CERN, and has been participating in the experiments since the 70s, and has collaborated, for example, in the construction of the Large Hadron Collider. You will see now what it is, and two of the most important detectors like CMS or ALICE. It has also contributed to several other experiments and operates 2 data centers of the computing grid. I have a use case for it, so you will see how it works. So, but what is CERN mission? So we can say that CERN mission is fundamental research in particle physics, and also is collaboration, international collaboration, to bring nations together. But there are also 2 other really important aspects for CERN. One is education, because giving training to the young people, to the students, to the young scientists and engineers, that is really important because they are the future. And also, another aspect that is very important is to advance in technology. You will see how CERN requirements are very unique. Sometimes you have to push the technology into the limits or even to develop new ones. But if we have to pick one of those that can define CERN by itself, that would be fundamental research in particle physics. But what does it mean? What is it exactly? Well, we try to understand how our universe works. So what is the universe made of? Or what is going to happen in the future? How is it evolving? What happened just at the beginning of the Big Bang? Things like, why do particles have mass? That is a good one, because we knew they have mass. We could measure the mass. What we couldn't is explain why they have it. So if you like physics, or maybe you saw it in the news, 2012 was a major milestone for physics. It was announced at CERN the discovery of a new particle. That particle turned out to be, later on confirmed, a Higgs boson. Why is that important? Well, the Higgs boson can explain why particles have mass. This is a reconstruction of an event in the ATLAS experiment that is a candidate to explain the Higgs boson for the discovery. So I'm sorry, because it seems like it's too bright, and maybe you don't see exactly what it is, but I explain. The standard model in particle physics is our best understanding of how all the elementary particles and forces work and are related to. The elementary particles are the most fundamental parts where the matter are made of. So we discovered the Higgs boson, and then you can add it there, and you completed the standard model. So you might think that maybe, okay, now this is explained, so everything is finished, perfect. Well, not really, because there are many things that this standard model doesn't explain yet. So we have to continue the discovery and the research. Like, for example, what is the 95% of the universe made of? we only know 5%. All the matter we know, all the matter we can touch or we are made of, it's only 5%. The rest, something called dark matter and dark energy. And they are called dark because we cannot see them. So you might think that, okay, so then how we know it exists? Well, we know, for example, in the case of the dark matter, because when we observe the stars, you can you can see that they are moving much faster than the gravity laws predict. So then you infer the existence of something else. But it's not the only one. Like, for example, why is there is far more matter than antimatter in the universe? Because at the Big Bang, it should have created equal amount of them. You know that when matter and antimatter enter into contact, they annihilate, releasing a lot of energy. Or like, how was the state of the matter just after the Big Bang? It wasn't like it is now. It was a kind of hot, dense soup of particles moving close to the speed of light. And, well, CERN is like trying to going back more than 13 billion years to analyze how was it and to understand how it behaves. And there are more questions that we don't know how to answer. But you might think that, okay, how a physicist can study the state of the matter just after the Big Bang, or how can they study the antiparticles? So that's why at CERN you have the accelerators and the detectors. The accelerators boost particles to high energies and high speed, and then make collide them. Can be with fixed targets or with more particles. And then the detectors observe those collisions and record everything that's happening there. The most famous accelerator is the Large Hadron Collider. This is not only the largest accelerator, but also the largest machine ever built. It's 27 kilometers circumference, and it is placed in the border between the canton of Geneva and France. There, particles are accelerated to really high energies and very, very close to the speed of light. It's at 99.999999% of the speed of light, and creates up to 600 million collisions that generates in raw data 1 petabyte per second. Of course, 1 petabyte per second is impossible to manage, so there are a sophisticated triggering filter system that selects only what the physicists want. But they are not the only facts. It's quite impressive, and I really like the one that is one of the coldest places on Earth, because the main magnets have to operate very close to the absolute zero. And also at the same time, is where it has recorded the hottest spot in galaxy. When they collide heavy ion particles, you can get the temperatures 100,000 hotter than the center of the sun. By the way, you know why it is underground? Somebody can guess why? Well, it is in fact because it was cheaper underground than in the outground. I mean, because Geneva is a very expensive region, and if you have to buy 27 kilometers ring, that is a lot. So when collisions happen, detectors like the Atlas record everything and observe everything that's happening. Atlas, this one in concrete, has around 150 million sensors, and you can think that it's like a giant camera, 3D camera, taking more than 40 million pictures per second, generating also really high data rates. And those are not the only one. This is the accelerator complex, the CERN accelerator complex. So in fact, it's a chain of accelerators where particles are accelerated incrementally in each of the accelerators. When they get the maximum energy in one of the smaller accelerators, they are injected into the next one. The last step in the chain is the Large Hadron Collider. Yeah, we have. This is the Large Hadron Collider, and the particles are usually injected at the beginning of the chain through the linear accelerators. And there are more experiments, not only the Atlas one, but also in the LHC, for example, you have ALICE, CMS, for LHCb, and there are other experiments around the whole accelerator complex. So you can imagine that this is not an easy system to control and has many, many complicated and critical systems like cryogenics or vacuums or machine protections. And you have millions of sensors, you have large number of control devices, you have also to deal with all the specialized equipment. So there are many challenges here. We can say that CERN is an extreme data environment in the sense that it's not only physics data, that we store around 30 petabytes per year, but you have also all the data coming from the controls and operation of those accelerator complex, those millions of sensors, signals, the large number of control devices, all the equipment, all the front-end equipment. And apart, you have also the monitoring and logging system from all. And you can't forget about the supporting IT infrastructure. It's needed for this to work. And you have a lot of databases, a lot of different storage systems, network services, etc. CERN has made a great data investment in the sense that we have very nice and great monitoring and diagnostic tools, and we have been storing that data that they gathered for many years. So, for example, the accelerator logging service generates around 275 gigabytes per day, and that data is stored, from that data we stored like around 50 terabytes per year. And it comes from the data acquisition from the whole accelerator complex, some part of the experiment, and other systems. And there are defined around 1 million signals. So the signals are like temperatures of the equipment or the sensors, like vacuum pressures or electrical current, etc. So those systems are very important to understand what's going on in your systems, right? And in case there is something wrong or there is something that you're not sure, you can go there and see and try to analyze if something is happening. But sometimes you can't avoid the faults, because when you detect something, it's already too late, and you have to realize a corrective intervention that you decrease the availability of your system, in this case of the accelerators or the detectors, for running what you really want, that is physics. This chart shows, for example, the corrective interventions of the Large Hadron Collider in 2012. Not all of them stopped the accelerator, not all of them, but they are corrective interventions that you have to do, right? So taking that into account, if we look a little bit into the future, the Large Hadron Collider upgrades will further increase the luminosity. Luminosity is the number of collisions, and with the number of collisions, you can think that you increase also the computing resources needs, and also the data generated will be higher. This year, for example, the ALICE experiment, if you can see it very well here, passed in the first round of the LHC was generating around 500 megabytes per second, and now it will generate more than 3 gigabytes per second. But even more, in the future, next accelerators might be much longer and much larger than the LHC. For example, the future circular collider could be around 80 or 100 kilometers long. So now if we take that we can avoid faults, and we see how is the future, because it's not that we are going to generate more data. Okay, it's that as soon as everything gets more sophisticated, it is more difficult to control and to analyze and observe if something is going wrong. So we can maybe scale everything that we have now. We have to find new ways to improve our systems. And that is what we are trying. We are trying to move from monitoring and diagnostic systems to something that is more predictive and proactive system that can give you information before it actually happens in your system. And that is where our data analytics plays an important role. So that is the project about. I mean, we are trying to optimize our systems, and we would like to reduce and to predict faults before they actually are in the system. So we can avoid the corrective intervention and increasing the availability of the services. And we would like to profit from the CERN data investment. We have a lot of data, and we think that we can extract knowledge from it to extract useful information that can help for suggesting conclusions and support the decision making. So at the end, what we would like to have is monitoring and control monitoring systems that are proactive, predictive, and in the last step, intelligent or smart. Of course, this is easy to say, but it's very difficult to implement, not only at CERN, everywhere. But at CERN, we have also some challenges that maybe not everybody has. We are a very dynamic and heterogeneous environment because there are a large number of projects with very different needs, different backgrounds, like physicist project or computing projects. You can think about many, many different things with different technologies, a large number of technologies, and data sources are also completely different and sometimes can be structured, non-structured, and from a different point of view. So the large amount of data we have, and I said, like, also not the large amount, but also the types, the kind of it is mixed with everything. And the education and training is another of the challenges. You can think that the experts on the system are who really know the data and their system, and they can understand how it works. Sometimes they even know what they want to do. They know they want to improve the system and to have something more predictive, for example. But they don't know how. They don't know the techniques or don't know how to establish that and to get that useful, that insight from the data. So that is something that we would like to help them to achieve that goal and to help them to use their data to have something more intelligent or smart, optimized. And another of the challenges we have is we'd like to create a kind of analytics as a service, some analytic platform that can have a complete stack of technologies or tools and techniques, so the users can find, for example, all the data management, all the data they need in an easy way, and also to go adding new modules in any place. They could be, for example, like traditional analytic solutions, or also something more like visualizing the data or discovering the data. So just to comment a little bit what is the CERN Open Lab. So the Open Lab just is a public-private partnership between CERN and IT leading companies. It is a collaboration, a nice collaboration, because for the companies, CERN is a laboratory, a very good laboratory. CERN gets also the knowledge and profits from the companies